Hello, Discrete Math class. Recording a quick, I say this would be 10 minutes or 15, review of occupancy problems. Did I teach this properly the first time? Kind of. There was a fire drill, and then I just kind of like assumed everyone knew everything, but maybe they don't. So it's never too late. I'm just gonna do all 8 of these and give like very quick explanations. Objects, indistinguishable. Containers, indistinguishable, not empty. What's up with this? Well, this means we have n rocks, totally undifferentiated rocks, just like plain, spherical, unmarked, black rocks. And that's because the objects are indistinguishable, the containers are indistinguishable, so that means we're just putting them into piles, and no pile can be empty. Well, this is P and K. By definition, that's what P and K measures, the number of ways of putting n rocks into k piles. No pile can be empty, so okay, great. Next, now we have objects indistinguishable, containers indistinguishable, but this is a terrible board setup here, but they can be empty. Okay, so here piles now no longer seems to sort of make any sense, so instead it's nice to have bags, but indistinguishable containers. So you just have some plain unmarked brown paper bags. Our objects are still indistinguishable, so it's a pile sort of can't be empty. That's my understanding of pile. But now I have n rocks, again, plain spherical black unmarked rocks, and we have k, brown paper bags. But now it is possible to put no rocks into a bag. And so now we have kind of like 2 answers for how to do this. The simplest answer for how to do this would be to realize that if we don't have to use all the bags, then don't use all the bags. P N1 is the number of ways of putting all the n rocks into just one bag. Pn2 is the number of ways of putting all the rocks into 2 piles, 2 bags. Pn3 is the number of ways of putting all the rocks into 3 bags. And we go through sort of, I guess I'll just do this. We go through by doing sort of casework on the number of bags used. Okay, so great. That is a perfectly fine answer to this problem. It is also possible to answer this problem with Pn plus k. And this came up, I think, sort of spontaneously or something. I can't remember what happened this year. But anyway, this was a homework problem in a slightly different form, was to prove that this is true. So it's definitely something that we need to know. Why is this true? Well, we can just give a combinatorial proof of it, and it's simplest if we give the combinatorial proof using the setup that we already had. And how did we do this? We said, okay, it's a little bit awkward, but we can make it work. The left-hand side counts this sort of by definition, so it's the right-hand side which needs some kind of explanation. And now we kind of, we borrow k rocks from our neighbor, temporarily. So in order to aid our organization or something, I'm like, yo, buddy, give me k rocks real quick. I'll give them back to you in 5 minutes. And now I have n plus k rocks, although I got to give k back in like a minute. And so, I just happen to know what Pn plus k is. What does that represent? It's the number of ways of putting n plus k rocks into k piles such that none of them is empty. So now I have distributed the n plus k rocks, my original n rocks plus the k that I borrowed, into k brown paper bags, but none of those brown paper bags is empty. So, okay, but this is going to include perhaps some cases in which there's only 1 rock in the bag. And so then having done that, since there's at least one rock in each bag, I can then take one rock out of each of the K bags. So now I remove the K rocks and give them back to my friend, thus leaving perhaps some bags empty. And therefore, one can view the left-hand side, of course, these numbers that we're incrementing by 1, 2, 3, K, etc., refer to the number of bags used, and refer to the number of bags that are used. Maybe I'll just stop there. That seems to do the job. I mean, is there anything else to say about this? Nah, we're good. Okay, keeping it moving. Going way too slowly already. What about objects? Distinguishable, containers indistinguishable, not empty. So now, what's going on? Yeah, the objects are distinguishable. So now they are no longer boring rocks. They are like, exciting rocks. So now we have like n different colored, shiny rocks, all of which are distinguishable from each other. The containers, however, are still indistinguishable, which means we are just putting them into K brown paper bags, and none of the bags can be empty. Okay, well, this is the exact thing that the Stirling numbers were created for. Stirling numbers of the second kind are, by definition, count the number of ways to put n distinguishable objects into K indistinguishable containers such that none of them is empty. So the answer to this is just S and K. Okay. And finally, squeezing it on the bottom here is objects distinguishable, containers indistinguishable, but now we are permitted to have an empty bag. Okay, so there's no really good way to do this. I'm putting rocks into colored distinguishable rocks into bags now. So I kind of want to use the Stirling numbers, but since some of the bags can be empty, I just have to partition by the number of non-empty bags. And so this is going to be SN1, the number of ways of putting all the different rocks into one bag, plus SN2, the number of ways of putting all the rocks into just two bags, plus SN3, the number of ways of putting the rocks into three bags, and all the way up to, such that none is empty, all the way up to SNK, the number of ways of putting the rocks into using all K bags. Okay, that's pretty clear. Let's pick it up now with the next column. If you have this worksheet in your hand, that's why I did it this way. Objects indistinguishable, containers distinguishable, not empty. Okay, not empty. All right, so, all right, well, at this point then, we might as well consider ourselves, if our containers are distinguishable, we might as well consider our containers to be people. Okay, and so really what are we doing? We have n boring rocks. When I say rocks, I mean the kind that are just black and spherical, unmarked, all exactly the same. And the containers are distinguishable, so what I really have are K different people who all look different, and I'm going to hand these rocks to people. And okay, none of them, everyone must get at least a rock. Okay, so there are two ways to do this. Method number one, which is probably the simplest, I suppose. Way one is to just say, all right, look, if no container can be empty, that's another way of saying that everyone must get at least one rock. So if everyone must get a rock, then it's kind of like step one, give each of the K people a rock. And if I give each of the K people a rock, then I have n minus rocks. N minus K rocks left over, n minus K rocks left over. And now I can do whatever I want. And by whatever I want, I mean I've met the condition that it was empty, so now it's up to me to distribute the remaining rocks any way I choose. And the sort of any way I choose means that I can think of these people, and there are K of them after all, A, B, C, D all the way up to K, etc., as standing there. And now I have my remaining N minus K rocks, and I'm just going to put them in piles at their feet. Okay, this is exactly the kind of thing that stars and bars was designed for. So we think of there as being K minus 1 bars separating the K different people. And then I am just putting, rocks. Some people are getting rocks, some people are getting no rocks, some people are getting a lot of rocks or whatever. So the number of ways to distribute the N minus K stars in and amongst the K minus 1 bars gives a string, and the length of that string is, I have N minus K stars plus K minus 1 bars. So the length of that string is N minus 1, and I am choosing, choose K minus 1 is the number of ways, it's the number of strings of length N minus 1, K minus 1, consisting of N minus K stars and K minus 1 bars. And every distinct string of length N minus 1 consisting of K minus 1 bars and N minus K stars is a different way of distributing the remaining N minus K rocks. Okay, this is like fine, but perhaps it's like a little bit convoluted. Maybe it's actually kind of simple because it follows up on something that we already know, which is the stars and bar method, but it's possibly worth it to talk about way 2, which is kind of like more direct. Way 2 says, okay, well, if no one can if everyone must get a rock, then let's think of the rocks as already there. So here we have N rocks. So I'll just go like rock, 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 and we have N of these. So here we have these N rocks. And if those are the N rocks, then there are spaces between those rocks. Specifically, we have N minus 1 spaces. N minus 1 spaces. And then it's time for me to divide up the rocks among all the people. Well, to divide up the rocks among the people, I can just place bars into the spaces. There are K people, so I need to separate those K people with K minus 1 bars. And so some, but not all, of the spaces are going to be filled with bars. How many bars? K minus 1 of them. And every bar is going to be interpreted as a divider between the various people. So here A gets 2 rocks, B gets 1 rock, and then et cetera, et cetera. So, and then the last bar, well, then it means that K is getting just 1 rock here. Okay, so since you're only allowed to place a space between rocks, then the closest you can place to bars is on either side of a rock, therefore everyone gets at least 1 rock. Okay, and so the answer then to this problem becomes, hey, you just have N minus 1 spaces, and into those spaces you must place K minus 1 bars. Well, there are, and this is what I meant by direct, N minus 1 choose K minus 1 ways to fill the N minus, to choose which of the N minus 1 spaces will be filled with bars. Because you have N minus 1 objects, the objects are the spaces, you have K minus 1 things that you are sort of picking, and you're picking which of those K minus 1 spaces will be filled with bars. All right, good. I think the rest of these are now a little bit easy, maybe. Here we go. Objects indistinguishable, containers distinguishable, empty. Okay, so now what do we have? Objects are indistinguishable, so we still have N rocks. They're still just undifferentiated, simple black spherical rocks. The containers are distinguishable, so we still have K people, but now some people can just get nothing. So if some people can just get nothing, well, this is like the original stars and bars from back in March. Now we have, in a kind of a straightforward way, or at least a familiar way, we have the people all lined up. Here they are, A, B, C, D, all the way up to K. and we think of the spaces in between those people as being divided up with bars, and so we have k minus 1 of these bars, and I have my n rocks. Well, now I'm permitted to give people no rocks at all. That's what this means, and so I'm just placing my stars here. B gets no rocks, but C gets 1 rock, and K gets, say, 1 rock or 2. Okay, so every different string of length, well, I have k minus 1 bars, and I have n stars. The stars are just rocks, and so I have n plus k minus 1 characters in my string. So n minus k plus 1, choose n is the number of ways of making a string of length n plus k minus 1 consisting of k minus 1 bars and n stars. Yeah. Good. Kind of just like zoning out for 1 second, but I don't need to zone out. Good. All right, next, last two. And then we are done. Here are the last two. Don't like this. Don't like this. These boxes that I've been doing. But okay. What's going on? Well, now we have objects distinguishable, containers distinguishable, not empty. Now this is pretty easy, I think, but there was a fire drill now, so we never talked about this in class. And yeah, what do we know? Well, the objects are distinguishable, so that means that we have n different colored, rocks, and all different colors, and we also have k people. But this time, everyone has to get a rock. Well, if everyone has to get at least 1 rock, then it's sort of can be thought of as a 2-step process. Some people are going to get, multiple rocks. Some people might just get 1 rock. And so yeah, I have sort of, k goodie bags to concoct. And then after making my goodie bags, I have to decide who gets which goodie bag. So once you think about it that way, then you can realize that it's kind of a follow-up to the problem that sits immediately to the left of it. Here we had n different colored rocks, and we had k brown paper bags, and the answer was SNK. In other words, here we are merely preparing the bags, but here, because the containers are distinguishable, we are also distributing the bags. And therefore, there are S and K ways to decide which shiny colored rocks will go in bags with which other shiny colored rocks. And now I have my K bags. All those bags are different. So for every way there is to make the K distinct bags full of rocks, non-empty bags full of rocks, there are K factorial ways to distribute those K bags to the K people. So first I make all the bags, and then having made the bags, and there are this many ways to do it, I then, there are sort of K factorial ways to permute those bags, to pass out those bags, so to speak. Okay, and now the final one, objects distinguishable, containers distinguishable, empty. All right, this one is the simplest one of all in a kind of a sense. What are we doing? Well, we have n different colored shiny rocks, each one special in its own little way, and we have k people. But now, we are permitted to give somebody nothing. And if permitted to give somebody nothing, then it means that there are just no rules whatsoever. I can do whatever I want. In fact, I could just give all the rocks to just one person even. And so once you think about it that way, then what you want to do is you want to sort of take it on a rock by rock basis. First, colored rock, say the purple sparkly one, who should I give the purple sparkly rock to? You just kind of pick them out of your bucket and you're like, oh, I'll give it to, person H or whatever. So you have K choices for who to give rock 1 to. Okay, now comes the red rock. Well, I have K choices for who to give the red rock to as well. And then for every single rock, I have K choices because I can give it to whoever I want. And so the answer to this problem is just K to the N, because for each of the N rocks, I have K choices of who gets it. Okay, that was like probably pretty good. So good, goodbye.